So I'm here today presenting my first place solution for the Yale competition. About me, I'm Harshit Sheoran. I'm bachelor's in computer science. I'm Kaggle competitions master. At this time, I'm ranked 13 on the global leaderboard, and I've won prizes in 11 computer vision competitions in the last 2 years. Today's we are going to be discussing about how I did processing data, model architecture, training and how I scaled it, generating more data, and finally, pseudo-iterative training. Starting with the data processing. So the data that was provided was in shape 5,1000,70. Uh, I did a simple technique where I concatenated the 5 channels into the spatial dimension that was lacking pixels, so 70. That made the shape to be 1000 times 350. And here are some visualizations about like how it looks like. So each of these is a channel, each of 70 pixels is a channel, but we have them like in just one image. So this is like to achieve more image-like data. I started with simple like vision transformer architecture. The model of my choice was an EVA02, a small. EVA doesn't stand for anything, but this is a very, very good model like available in the TIM library, one of the best ones. So I started with it. My architecture was actually on the right side of the screen. It's that I'm giving it an image. So for this like batch size, and because we don't have like 5 channels, we concatenated them into one. So one, and then we have 350. This first 350 is just 1000 resized to 350, and the second 350 is the 17 times 5 equal to 350, which then gets passed on to a vision transformer model. The transformer's outputs batch size, 625 plus 1, where this plus 1 is actually the classification token. Not every vision transformer outputs it, but some do. If the transformer is outputting this token, we just drop this token because it's not to our use. And then in the final dimension, we have the embedding dimension. Then I use a linear layer to convert this embedding dimension to 14 squared. Where does the number 14 comes from? 14 is actually the patch size which the vision transformer used. By this, I got an output of batch size, 625 and 14 squared, which then I can reshape to 25, 25 because 25 squared is 625, and 14, 14 I transpose it to look like this, and then I reshape it to the original image size, and that's my output. The result was about like quite impressive. It was 30 MAE with just 40 blocks of training, really simple to train, really easy to make. Probably like first or second day of the competition, I had this. This is like where my baseline started. What I spent a lot of time on was searching for a decoder. Traditional UNet decoders or convolution decoders were a poor fit. Like I had this intuition because the input-output pixels, they don't have the spatial alignment that is usually present in computer vision tasks. So I actually tested a wide variety of decoders: UNet, UberNet, Mask2Former, VIT adapter, more, but they are less known. But yeah, the result was the same, that none of them improved my score. The breakthrough idea was that randomly, this was not even like a huge idea. Randomly, I tried just adding a second vision transformer ahead of the first one. And this gave me like more boost than just simply scaling the model to a base variant or a large variant. This is what the architecture looked like. The first part is exactly the same I just explained it. And the second part is also like exactly what I just explained. So what I'm doing is like first part, and then I'm just repeating it again. And this improves the CV from 30 to 28. Because my GPUs were like kind of chilling out at that point, this actually did 2 times. It did less than 2 times. It took me less than 2 times to train. So it was also efficient. Then the question came like, why is EVA model specifically like outperforming the standard VITs? And it's also like slower. It was actually outperforming it like by quite a bit, like 3 to 4 ME on the same set of training. So what I did was I tested model depth, number of channels, attention heads, MLP scaling, gated attentions, like basically everything that was possibly making something faster or slower, or like that was different between the standard VIT and the EVA VIT. I tested them one by one. I tried changing them, and I saw that how much this impact on the score is. The single biggest factor was actually rotary positional embeddings. So what I did was like I took a really good VIT small model, and I modified it with rotary positional embeddings, and that's my final encoder and decoder setup. To explain rotary positional embeddings, this idea comes from natural language processing. Basically, LLMs use it. The mechanism is, instead of like the absolute positional embeddings that the standard VIT uses, where we add a learnable vector to the patch embedding, rotary positional embeddings actually it calculates relative position, and then we add it to every attention. It's not simple as just adding it. Sorry, I chose the wrong words. Absolute positional embeddings adds, like we simply add the vector to the patch embeddings, but rotary positional embeddings, we give the vector with the attention. That's like, so every attention gets the normal embeddings and then the rotary positional embeddings, and it learns at every attention. The implementation is complex, but the results were much better. This was the final model architecture, where it's basically the same, but now both encoder and decoder share a rotary positional embeddings, and both models have a shared linear layer that does dim to patch size. This is done so that the first model does not create absolute BS, and there is like something to guide it, like something to forcibly guide it. And then the output, of course, gets bilinearly resized to 70 times 70 because that's our target, and I'm using MAELOS. Training this approach, I always trained with about like 1e minus 4, and I cosine it down to 1e minus 5. This is the learning rate. Then the optimizer is AdamW. I tried a lot of them, but did not work better. Loss was a classic mean absolute error. I did add horizontal flip in time of training. 50% of my samples gets randomly horizontal flipped, and a test time augmentation to benefit from that horizontal flip at test time. Then exponential moving average, and I progressively increased the image size and training more epochs. This was basically a necessity to get the model to training longer leads to better results, and increasing the image size makes sure that the model does not converge too soon. Similarly, like this is my first full scale training, which is image size 350 times 350. We train for 100 epoch, 22.3. We continue the training, but this time we increase the image size. And then we train for another 100 epoch. We converge to 18.57. We continue the training. This is not resetting. This is continuing the training. By increasing the image size 588 times 588, we get a even lower. And then 700 by 700. This is where like the limit of my GPUs came. And honestly, like the score is getting less and less better. So yeah, this is where like pretty much the point where training more is not helpful. 16.21 is far from like what we are expecting from top places. So here is like main part that is pushing the score ahead. Generating more data is something that a lot of solutions have done, and it is like really helpful. The challenge was to first find a forward modeling function that replicates the original dataset, and then make it a lot faster to be able to do it really fast. I tried generating more velocity models through heuristics, but they were not successful. So I ended up just augmenting the augmenting the validation, the velocity parts, and just showing is more helpful. So over the 5 original samples, then this is basically the cropping of this. We are cropping, and then this is the random FI. So we are randomly changing the. So we are adding augmentations basically on the velocity maps. So training and scaling, this one is actually, this is the same image you saw from the previous one, but the down here is the same training, similar training, but with the synthetic data pre-training. So instead of adding it directly into training, I actually pre-train on the data set that I made here. And then I have, I fine tune on this parts. So I'm fine tuning on, I'm pre-training for 5 epochs, I'm fine tuning for 50 epochs, and this leads to like much better score here. And continuously, this leads to much better score here, like training for about just like the time how we did here. We are actually converging to 11.77 instead of 16.22. And iterative pseudo is basically my term to say that for each epoch, I'll use the model to predict the test set and my validation set. I will add I'll forward model those like the samples, and then I'll re-add them to the training. Reading the text on the screen might also be like very helpful right now if you are like having trouble understanding me. I'm sorry. First, we train the model like we did on the previous step. Then we predict the text sample and the validation. These are our pseudo labels. We forward model them to get actual new synthetic input data. Then we pass the synthetic data and pseudo labels to train the next epoch. And this cycle repeats for every epoch. And this is the final training and scaling, how it looks like. So everywhere that is this yellow color actually has a pseudo iterative built right in. So we are converging just non-stop, like no matter how we can just train forever and forever and forever, and it just does not want to stop converging here because it is continuously like getting the correct. It is getting the pseudo iterative steps, right? And the last small trick is selective training. So I noticed that only 4 of the methods were actually making an impact. So I only take those samples and removed over half their data and just allowed the model to hyper focus on them. And then I blend the predictions where I choose the 6 standard methods from the general model we trained, and these four methods are chosen from the specialist model. And this boast, so the progression is like our baseline is a standard VIT model. A perfect architecture gets the score down to 25.8. Just scaling that perfect architecture gets to 16.21. Adding the synthetic data is 11.77. Pseudo training is 7.94, and the final blend is 7.5. Thank you.